So I've already talked about some units in, well, space. One important thing in most physics problems is having a coordinate system. If you're launching a moon base, you want your rocket to know which way is up, or your moon base is going to end up in Australia. Celestial coordinates is one that uses the Earth as its reference. Ish. Globally, we have latitude and longitude. In celestial coordinates, the latitude equivalent is declination, and it starts where the equator of the Earth would normally be projected. The longitudinal equivalent is called Right Ascension, spreads similarly to a globe, however we don't have a Greenwich? We don't have that meridian to use as a starting point. But if you remember from not being born before 1576, the Earth orbits the Sun. This motion doesn't happen on a flat disk, because realistically, everything is frigging moving. Now, because the Earth is tilted, the plane of its revolution does not line up with its equator. This means, looking up, the Sun will trace a path that isn't in line with the equator. This is called the ecliptic, and it's about 23.5 degrees angled from the starting declination, and where they intersect will be taken as a 0 point for a right ascension. Of course, there are two intersections, but fun fact, all 12 signs of the zodiac appear on the ecliptic. One of these intersections lay in the constellation of Aries. No, Aries the sheep. Oh, well, never mind. Apparently I'm still living 2,000 years ago. It's now in the fish. So we have a starting as we go above or below the equator for declination, and another as we go around the... I'm going to call this the fish intersection, as we go around the fish intersection. But astronomers seem to have an allergy to normal, so instead of using degrees for right ascension, they use hours. The celestial sphere rotates around the polar axis by 15 degrees in 1 hour, so they use units of hours, where 1 hour is 15 degrees. And there we have it, celestial coordinates derived from the Earth, and the Earth's rotation, and the Earth's revolution. But the Earth doesn't spin perfectly stable. Due to the gravitational dynamics of that ball of dirt, and our ball of dirt, and that ball of dirt, it wobbles. So the poles and its orientation aren't always pointing the same way. So with time, right ascensions and declinations will change. Current conventions though use coordinates defined from the year 2000 and accounts for that. Now, one thing I should have discussed last time was brightness, since we're looking at the sky and it's light and stuff that shoots lasers at us. So we can take brightness in terms of kilogram meter squared per second squared per meter squared, or a watt per meter squared, or we can use a magnitude scale. See, if I give you these 4 stars that are incrementally brighter than the previous, you'll say, cool. Then if I give you these stars which are exponentially brighter than each other, you'll say, you know there's medication you can take, right? The point is, our eyes don't see linear brightness, they notice magnitudinal differences. A star that we'll say has a magnitude 5 times less, I'll get to that, is actually 100 times brighter. One Greek guy, Hipparchus, made a brightness scale such that the brightest star will be of the first magnitude, and then the second brightest will be the second magnitude. And then 1800 years later, Pogson put that into an equation solidifying that order, meaning smaller magnitude, brighter star. Yay. There is the added benefit that if we take the magnitudes of different wavelengths, specifically the blue and the visual light, we can get a BV color index. This tells us how blue or red a star appears. Not that kind of blue or red. I'm summarizing this a bit much, but we can ignore most of this until we're ready to start using it in applications. One thing to consider is how intertwined all the different branches of physics are in astrophysics, but with like the knob turned up to 11. For example, the vacuousness of intergalactic space. Wait, what does vacuousness mean? Oh, holy crap, that's me, I'm vacuous. Anyway, the vacuumness of intergalactic space is more vacuumy than our best vacuum. But it's not just the big stuff that astrophysicists look at, but the really small ones as well, such as the mass limit for white dwarf stars before they become black holes. This is derived to be... but we're not touching that. One thing that I find funny is the author of this deck specifically states that he's going to assume that the reader has a working knowledge of mechanics, electromagnetism, thermodynamics, and quantum physics at an advanced, undergraduate, or beginning graduate level. Well, he's wrong. So, we'll get to that eventually.